everybody, or good afternoon, or wherever you're at. Uh, my name is Steve Higgins from Rolls Battery Engineering. I'm the Technical Services Manager at Rolls Battery Engineering, and I'm here today to present a webinar for you on some basic concepts for off-grid storage or flooded battery, flooded deep. Hope everybody can hear me. Just a couple things about the interface. Uh, on the right-hand side of the screen, there should be if you're looking at it through Google, you should be able to have there's a chat room there. There's also a question pane there if you want to ask questions. Feel free to ask the questions. Everybody's microphone has been muted, so we don't get an echo. I have about 32 slides, should be about 30 to 40 minutes at most, and then we'll do a question and answer session. Make sure there is a delay, about a 15 to 20 second delay. So by the time I get past something, more than likely you'll have a question for it, and just make sure you go ahead and answer the question on the pane, or you can email me directly at steve@surrett.com, and we'll get your questions answered. To go on. Oops. There we go. So having some technical difficulties here. I apologize. This is the first time we've used this one. So just some battery bank facts. Very important to understand. 12 volt, we typically operate 12 volt, 24 volt, 48 volt systems. A battery, a typical flooded lead acid battery is made up of 2 volt cells, 2 volt blocks. So a 12 volt battery bank has 6 cells, 24 volt battery bank has 12, and a 48 volt battery bank has 24 cells. So when you call us to talk to us about what you want your batteries to be charged at, or voltage parameters, we typically will discuss this with you at voltage per cell. A nominal charged, a nominal voltage for a battery, for a flooded lead acid battery, generally is about 2.13 volts per. That means that if you have a resting of 12.78 or higher, with no load, that means that you have a full charge on your batteries. A discharge battery that's at 100% rests at 1.75 volts per cell, and that's basically your LBCO settings for most of your inverters, or 10.5, 22, or 44 volts on a 44 volt system. What causes a lot of problems with a lot of customers is when you have a resting voltage of less than, say, equal to or less than 2 volts per cell, that means your batteries are at 50% depth of discharge. That coupled with specific gravity checks should confirm that. Just an important note, flooded lead acid batteries, depending on the cycle use, really need to be fully charged. You need to see a full 1265 to 1275 specific gravity about once every 20 to 30 days. If you have systems with higher cycle, so if your customer is cycling their batteries, a couple times a day, or a couple times, once every single day, they may see better performance if they make sure they get those to a full charge about once every 2 weeks. Valve regulated acid batteries, gels, and AGMs need to see a full charge about every 6 to 7 days, and this is because they're technically considered acid starved batteries, electrolyte starved batteries, and they need to see that full charge. This is a very important thing this is a very important state to understand. Most customers don't know it, but batteries just don't die. In most cases, they're murdered by the customers, by the end users. And what I mean by this is most often customers or installers alike aren't properly charging the batteries. It's very important to understand the entire charge process. As a battery manufacturer, most battery manufacturers really only care about 2 modes, your bulk and absorption time, especially for a renewable or off-grid system. Because in float, if you're an off-grid system, you're running your generator, when you hit float, your generator should be shutting off because you're not really doing much, you're not really putting much of a charge into the batteries at that point in time. The bulk stage is a rising voltage, constant current stage. This is an unmeasured time frame. Typically, your 1,000 amp hour battery bank with a 100 amp charger, you're going to spend between 35 and 60 minutes in bulk stage, maybe a little longer depending on the temperatures. Your absorption stage is where your current goes into the battery. That is where you absorb the rest of your voltage is already in your battery, and your current is slowly flowing into the battery. If you notice, this red line is voltage, the yellow line is current, and as the voltage comes up, the current's going to drop off. And it's not a linear drop off like this, but it'll most likely be a severe drop off at the beginning and then taper off down to the end. You want to be careful with that, because a lot of folks will assume if they have a 100 amp charger, they're going to have 100 amps in absorption, which is very rare. Typically, if you have a 100 amp charger into a 1,000 amp hour battery bank, you're going to drop into the 30, 40, 50 amp range. So the yellow line again is current, red line's voltage. So during the bulk stage, you have constant current, rising voltage. The absorption stage is a constant voltage with a tapering current, and then of course the system drops into float. So a lot of people ask me this: why is absorption time so important? The biggest reason that absorption time is important is you are allowing the last portions of the current to get into the batteries. If you never complete an absorption time, a proper absorption time, then your batteries are never seeing a full 100% charge, and you're actually causing sulfation, hardened sulfation on the plates, and you're losing battery capacity, and that's cumulative. So the longer you do it, the more losses you're going to have. A lot of customers will get a hold of me and talk to me, and they say, "Well, I have a state of charge meter which is using end amps, so I don't need to use absorption timers." That's actually an incorrect statement, because both the state of charge meter and the absorption times need to work together. Typically, ideally, if you have a healthy battery bank, using a state of charge meter and shutting off via 1 to 2% of end amps is more accurate. But if your batteries are unhealthy and you're still using that SOC meter, then what can happen is that you can go through your bulk stage too fast, and then you never really complete and absorb, and then so it just exacerbates the problems. Just to give you an idea, some basic information. Remember, bulk phase for all the inverter manufacturers today, inverter charger manufacturers, is untimed. They don't keep track of how much time that you're in it. When you reach your absorption stage, your batteries are only about 80% state of charge for a flooded lead acid battery. Okay, so when you hit this point, your batteries are only about 80% state of charge, but you start to lose current going into the batteries, and so current is tapering. So it's very important to use this formula. The time equals 0.42 multiplied by C20 rate divided by nominal current. That'll give you a basis of an idea where your absorption time should be. For example, just to make it easy on everybody, if I have a 1,000 amp hour battery bank and I have an inverter charger rated at 60 amps, and I have a solar array that's rated at 80 amps, and I'm going to get my average output of those devices, my absorption timers aren't the same for both devices because I have two different charging. Very rarely is your inverter on while you have solar, or if you have sun, most people aren't running their inverter charger unless they have a problem. So in this case, for a 1,000 amp hour battery bank, my inverter charger being at a 60 amp output nominal, if I have a 60 amp output nominal, my absorption time for my inverter is 7 hours. With that charge controller, I'm looking about 5 hours and 20 minutes, because I have a little bit higher charge source. The problem with that is that in most places, that 5 hours is just the absorption time. That does not count the time in bulk. So in most cases, the solar array in this system will not fully complete a full absorption time every day. And then what you'll start seeing is deficit cycling on the battery bank. We go to a 1,766 amp hour battery bank with the same ratings, and now I'm looking at it running my inverter for 12.3 hours while my solar is at 9.5, 9.2 hours. this is not just something that we brought up. This is an actual system that a customer called, had problems with it, and didn't understand why their batteries weren't being properly charged. So some things to keep in mind: charging parameters, lower voltages, shorter absorption times, the batteries remain cooler. You maximize your service life, but sulfation is going to occur and will require more frequent equalization cycles. The slower charging times, it's going to cost you more fuel, more energy, more solar, more renewables to keep those batteries charged. Higher voltage charging, you increase your charging times. Your capacity readings are more consistent. You've got less sulfation, but you have more gassing. You could have more corrosion on your terminals. You're going to use more water. And if you start seeing temperatures in excess of 115, 125 degrees, you're going to start seeing overcharging and or active material shedding. One of the things I always tell people when I'm talking to them, especially when it comes to charging their batteries, it's cheaper to replace distilled water than it is to replace batteries. So the gassing typically, yes, you're going to have to use more water. You're going to have to do a little bit more maintenance, but it's better to do that than to have to worry about running multiple equalization charges or basically having batteries that die after 3/4 of use anyways. So here's a chart based on our settings. Basically, there's two charts for the flooded batteries. I've got all the charts on this presentation. I'll skim through the AGMs and the gels, but this first chart is for this first chart is for partial state of charge or regular cycling. So if your customer's heavily cycling the batteries, or you're trying to recover the batteries from abuse, what you want to do is you want to set your bulk and absorption rates, your charge voltages, at this 2.5 volts per cell. You know, and typically what you want to do is you want to run that for 4 to 6 weeks and see if you can recover your specific gravities. Once you recover your specific gravities, you can drop that a little bit lower. Again, what you want to do is you want to look at your specific gravities on a quarterly basis, and make charging voltage adjustments. So based on how much load the customer's running, based on how much you're charging, and based on the seasons. And most systems, in April and September, you're going to adjust charging voltage settings. Customers who leave systems at one set point all the time, very rarely are going to have decent specific gravities year round. You might have great specific gravities in summertime, but they might fall off a little bit because your wintertime production is a little different than your summertime production. Again, these voltage settings are assuming that you're using, the ones in red are assuming that you're using temperature compensation. If you're not using battery temperature compensation, then that's a serious problem, because you should always be using temperature compensation. Without it, you're not properly charging your batteries. The next chart is an infrequent cycling or a backup system. So where this comes into play, and you may even, I've actually seen systems even a little bit lower than this, still running at good specific gravities, where if it's an off-grid cabin where the customer's out there once every couple of weeks or once a week, they've got all week to sit on solar and charge the batteries. So realistically, your charging voltages can be, you know, I can take 10 of the same system and put them into 10 different homes, and get 7 or 8 different programming settings, anywhere between 2.44 or 2.45 volts per cell, all the way up to 2.5. So again, the actual settings for programming vary for customers. The next few slides I'm going to go through pretty quickly, and so these are the AGMR and our tubular gel charge settings. I just put this in for reference, even though this is primarily a flooded battery discussion. Couple issues about sizing. Common sizing mistakes that we see out there. The number one sizing mistake would be oversizing the battery bank. The go big or go home mentality. It's not really the best thing. Typically what you want to do is you want to go to 1 to 2 days of autonomy, 3 days really at the max. Remember, the larger the battery bank, the charging requirements, the current requirements, the more charging time, you put in a 1,000 amp battery bank with a 60 amp charger, that battery bank is going to struggle to see a full charge within a reasonable amount of time. In the off-grid business, most customers do not want to see their generators run for more than 3 or 4 hours. They just don't want the fuel cost. To do that, you're going to need 15% of the C20 rate. So if you have a 1,000 amp hour battery bank, you're going to need a 150 amp charger to get below that number to be able to keep the customer generator runtime that low. Another issue that we see, too many parallel strings. Most experienced installers, 1 to 2 parallel strings max. 1 string, of course, is always preferred because you don't have the current drop off that you would normally have in 3, 4, or 5 parallel strings. Have 5 parallel strings of S550 batteries. That means I've got 120 cells to maintain. If I did the same installation with 2-volt cells, I'd have 24 cells to maintain. So most customers aren't going to check that, to check those, to do the proper maintenance that's required on batteries. Another issue is taillight installer. What I mean by taillight installers is that battery-based systems require follow-up. They require ongoing maintenance. If you're installing battery-based systems and you install it and you collect the check and you never go back and check with the customer or never follow up with the customer, or you don't offer a maintenance contract, basically you're leaving money on the table. It's a good idea to follow up, after an installation, 60, 90, 180 days out, and just talk to the customer and ask them how everything's going. Get them to email you a copy of their specific gravity records. That way you can double check, or you can send that off to us, or they can email that to me, and we'll be more than happy what they could do. Shoehorning product. This is pretty common, especially in Africa, Latin America, where lead times can be, an additional 4 to 6 weeks due to ocean transit. Is where you've got 60 L16s in stock and you got no 2-volt cells, and so you just throw in 4 parallel, 5 parallel strings of batteries and call it good. You want to try to make sure you plan for that installation, and make sure you have those. Don't let your customer force you that really shouldn't go into it. That goes into no system planning. Make sure you know product lead times, both inverters, charge controllers, batteries. Depending on the time of year, we can be anywhere between 2 weeks to 8 weeks, depending on the product. Summertime in North America tends to be a little bit longer lead times than in the winter time, just due to the weather and people using their equipment. Understand the product that you sell. Regardless of whose battery you install, regardless of whose inverters you install, you've got to understand and communicate with X. You can go look at 6 different battery companies, and because of the 6 different chemistries, you're going to have 6 different programming settings for those battery types. Don't ever, regardless of the battery, use the manufacturer's default settings for the inverters and the charge controllers, because if you do, I can guarantee you that those settings are going to fail. Be careful with that. Sure that your customers, make sure that everybody knows the system. Guessing load numbers. Don't ever assume what your loads are. If you do, I can guarantee you that, because when you're designing a system, you need to have a basic understanding of how that customer is going to use that system. Often installers, when they do a system quote for a customer based on their loads on a load analysis, they will make the customer sign and understand that they've designed it for this specific load profile, and if that load profile increases, that battery-based system will be undersized, and that'll cause problems. Last but not least is insufficient photovoltaic or renewable sources installed. All too often we get customers who have again that 1,000 watt PV array. If that's charging at 24 volts, that 1,000 watt PV array at best is going to do about 40 amps of current. 40 amps of current means that you're never going, if that customer ever discharges the batteries below 85, 90 percentile state, the batteries will never see a fully charged unless the customers run their generators. Again, it goes back to the customers running their generators. Often they will not run the generators for the length of time because they don't want to burn the fuel. Nowadays, with petrol or gasoline prices being where they are, it's a little easier. 5 years ago, when people were paying, $3 a liter, €2 a liter, in the States, $5 a gallon, it became more of a hard spot for people to run the generators. Another important thing to understand is and make sure your customer understands this also, is your discharge rates, or what we call the C rates. And what these are referring to is, like, for example, this is the S550 battery. At a 20-hour rate, we rate this battery at 428 amps. That's assuming a load of 21.4 amps of current. That same battery is a 554 amp battery at a 5 amp load. So a lighter load actually makes the battery last longer. A heavier load actually shortens the size or lessens the size of the battery. So if you have if you have a single string of L16 S550s and you're placing an average load of 42 DC amps across those batteries, you're really only going to get about 3.5, 4 hours of use out of those batteries. Now 42 amps of load, and say it's a 48 volt system, is really about 2,000 watts of power. So this is where it's important to understand that system sizing and to go back and fact check after you've done the installation to make sure that the customer is properly loading that system. In North America, we use North America and most of the rest of the world, we use C20 or C20 for discharge rates. Telecom systems would use a C100, and then in Europe, they typically use a C10 discharge rate. When you're recharging the batteries, you want to use about a C4 to C6 rate for charging. So ideally, if you want to be able to charge that 100 amp hour, that 420 amp hour battery between 42 amps and 60 amps, or and 70 amps of current. Again, that is to limit the amount of time that you spend in absorb. Nodal bank battery voltages. A watt is a watt is a watt is a watt. So these three battery banks, this 3,000 amp hour battery bank at 12 volts, this 1,500 amp hour battery bank at 24 volts, and this 750 amp hour battery bank at 48 volts. That's that is basically the same battery bank, same amount of power in those battery banks, just different voltages. The reason you'd use a 48 volt system over a 24 or 12 volt system is simple: copper. The cost of the copper is exponentially higher when you start using lower battery bank voltages, because you have to have more copper in the system to run the higher currents. So just be cautious of that. Something I put in recently, if you go through all the system, if you go throughout the entire system, and you total up all the loads, the PV modules, typical D-rate range, 80 to, depending on temperature, you're only getting about 80%. You can up to about 106, 110%. Charge controllers, 80 to 95% efficient. If you've got module mismatches, you're losing a couple percent out of that. Your connections, hopefully you're dropping less than 2%. For your AC/DC wiring kind of diodes or blocking diodes. You want to account for any kind of soiling or dirt on the panels as doing system design. Of course, battery efficiency. When you're in the bulk stage, they're taking a lot of current, but when you're absorption stage, you're you're only about 75% efficient, 60-75% of that at that time. And then of course, you've got shading and module degradation that you want to account for. So overall over the lifetime of the system, your total duration is about about 30%, 29-30%. When you're doing a system size, and this is just a general system sizing, there's two ways to do this. If I'm going to consume 15.75 kilowatt hours at 48 volts, say I take that 15,750 watts, divide that by, or add 15% for assumed losses, it's 18,112 watt hours. Divide that by 0.5, 1,224 watt hours of consumption. So for 1 day of autonomy, I'll need 36,224 watt hours of storage. Divide that by 48 volts. That tells me I need at least a 754 amp hour battery. Be careful using the current amp hour capacity wise, because that sometimes will cause people issues. So another way of going around that is doing the same calculations, but using kilowatt hours. So this is a different way of making those same calculations. So a couple systems, typical usage example. So you go out and you install a system. You've got let's say five hours of sun hours. You've got a 60 amp controller with a 3,000 watt PV array. Let's assume that your average installation is about 80%. So you're consuming that 17,500 watt hours. You're going to replace it every day, assuming we have good sun. You start with roughly 41,000 watt hours, and let's say the batteries are fully charged at the end of day 0. So you've installed it, your batteries are fully charged, you drive away. The end of next day, now your batteries, let's say everything was perfect. Now your batteries are down to 36,000 kilowatt hours of storage, or 36 kilowatt hours of storage. Your state of charge is about 86%. Okay. Your expected generator absorption time is about 5 hours with this PV array. If your sun's not working, your expected generator runtime is going to be about 240 to 300 minutes. Okay. At the end of day 2, now your state of charge drops below that 80% stage. Now you're looking at about a 6-hour absorption time on your generator, on your 60 amp and generator inverter charger. So what's happening is if you see, because of the size of the PV array being at over 3,000 watts on that 700 amp hour battery bank, the battery bank is now basically slowly declining. And no matter what the weather is, assuming you're getting full production from your sun, your PV array is not able to keep up with the batteries. Unfortunately, I see a lot of possible warranty submissions that are systems designed just like this. With the cost of solar the way it is, there is no reason not to over-design the PV array to be able to charge the batteries. So if we go to the next system, we just add another 1,000 watts of PV array, which would really only cost the customer, maybe $2,000, $2,500 after installation and mounting, maybe $3,000 at the most. Now we're only seeing a 4 or 5% drop per day. So that one battery bank will actually go 8-10 days before you have to start your generator. If you have to start your generator, run your generator 5 hours every other day versus running your or 5 to 6 hours every other day versus running it 5 to 6 hours every 8 to 10 days, which system do you think is going to cost the customer the least in the long run? Just common sizing mistakes. We had this system come in recently. I like to use real world examples. This one out in Maine, the customer had 36 4KS 27s in 3 strings, so he had a 4,300 amp hour battery bank, 4 SWs capable of doing about 300 amps of DC current when charging, and then he had a 72 100 watt solar 100 watt solar BP panels. So he had a 7,200 watt PV array. A 7,200 watt PV array, if you're not even considering losses, at 48 volts, at best is going to do about 150 amps of current, which means on 150 amps of current, your time is going to be in the range of 12 to 13 hours, which means in Maine, you're not even, unless the system's on a tracker. Actually, even if the system's on a tracker, you're never going to get that 12 to 13 hours of total absorption time to keep those batteries charged. So the customer is going to be running their generator quite often to keep the batteries charged. Here's another system. Customer wanted to do, this is the text on the bottom is what the customer was having, the issue the customer was having. Basically, by evening time, the batteries, the inverter would display a yellow lit error light. The sun shut back and it would go back to green because the inverter is displaying the inverters typically have a status light that tell you battery voltage. They don't really tell you the indication of so you want to be careful with that. This particular battery bank, the customer they'd used a bunch of 220 amp hour batteries in series parallel. They've got too small of an array. They had some issues with the system. So again, based on this setup, 4,100 watt hours, 2 kilowatt PV array, you're looking at you're looking at an absorption time of 8 to 9 hours. Again, if you increase the size of those arrays, your absorption times get to a more reasonable number where the customers can actually attain that full battery charge. So the next thing is the battery selection, what's model's best. So going back to that 754 amp hour capacity for 1 day of autonomy, if we're using a 48 volt battery bank, really here are your options. Here are the best options. You can do 2 parallel strings of S550s. That would give you a little bit higher amp hour capacity battery bank. You could do a single string of 6 CS25Ps. That gives you an 820 amp hour battery bank. Or this would be a much larger, and actually be about a day to 2 days of autonomy. 24 S1450s would give you 1125 amp hour battery bank and 1 series strings. These really would be your best options. You want to try to avoid, you really want to try to avoid going more than 3 parallel strings, because that's just gonna end up causing you and the customer problems down the road. If you're looking at multiple days of a capacity, then you would be looking at these 2 KS33s, 4 KS27s, 1 to 2 strings, and these would give you multiple days of autonomy. Again, once you go with these larger battery banks, you need to go back and look at how big your PV array is for charging. Because if you go and you say you stick with the 5 kilowatt PV array at 48 volts, you're only going to be doing about 100 amps of current. 100 amps of current charging this 1284 amp hour battery bank, your absorption time to be in the 5 hour range. So if you go with 2 days of autonomy, you may need to adjust your PV array to make sure that you can keep those batteries charged, or at least add an inverter in the installation for charging capability. So option 5, 32 S530s, 4 parallel strings, the 1700 amp hour. If we compared the two of these, the 2 KS33s and the S550s, the S550s would probably be cheaper in the entry, but in the long run, you're going to have balancing problems with these strings. It's not advisable to do these 4 series strings because you are going to have capacity problems down the road. It may not happen year 1. It's probably not going to happen year 2, but it will happen year 3 and year 4 where you will start to see capacity issues. I would stay away from that. So at this point, I only see 38 of you on the forum. I don't see any questions at this point in time. I try to keep these as quick. If anybody has any questions, now would be the time to put it in the Q&A if you have availability on the Google. If you're watching via YouTube, feel free to send me an email at steve@surrett.com, and I will be more than happy to answer your questions. I don't see any questions in there, so I'm going to go ahead and stop the. I'm going to go ahead and stop the broadcast. And again, I'll go back to my email address. I probably should have put my contact information. Yeah, go ahead and email me at steve@surratt.com, and I'll be more than happy to help you out with any questions you might have. Thank you very much.